Okay, first, in helping you do some of these problems on page 185 and 186, I'm going to select a couple of them, but first, look, factoring is going the opposite way. What we're really doing is taking a larger polynomial, which means, many numbers, obviously, and going the other way. Meaning, look, a plus b, times a plus b, we're going this way in terms of multiplying. So this is, if you FOIL it or rainbow it, it's FOIL is first, outside, inside, and last. So this is a squared plus 2ab plus b squared. So what is really important to keep in mind first off over here are these special factors in polynomials. This is one of them. Another one is, let's take both of these that are both a minus b, and if we multiply them and we say expand those, then same thing, we get a squared. And when you get negative b times a negative b, then the last term is also going to be positive. But what we're going to have here in the middle is minus 2ab. And then if we take the combination of one of these, this a positive and this a negative, then we can have a third example here of a plus b times a minus b. And this one's an interesting one because what we get is a times a, which is a squared, and we get negative ab. We do the middle one here and we get a positive ab, and we do the last one and we get negative b squared. Now that simplifies because these two terms drop out to a squared minus b squared, which you're really going to want to be able to recognize because that's called a difference of two squares, because we have a square here and a square here. The next important polynomial to recognize is on page 183. And on 183 they show a difference of perfect trinomials. So these are ones that you will want to be able to recognize by inspection. So again, recognizing by inspection is this up here, this one here, and the perfect square. Now, to go back to the perfect trinomial here on page 183, these are in expanded form: a squared plus 2ab plus b squared, and a squared minus 2ab plus b squared. Now, if we increase the factor here, if we change the factor, then meaning the number of times we multiply by these factors up here, then we get perfect cubes. And rather than 1, 2, 3 polynomials here, if we, and this is on page 184, then we get a to the third plus b to the third, or a to the third minus b to the third. So again, look at the similarity here, and I think this will help you. The similarity here is this is a sum of perfect squares, which is up here. This is a sum this is a plus b squared. Down here, this is a minus b. Excuse me, these are squared, not the outside here, but it is the same thing. Okay? I didn't do that very well, but please check your book. When you see this, these are perfect cubes that you'll also want to recognize by inspection. And you can have a card in this. When you see the sum of perfect cubes here, this factors to a plus b. So in other words, take the root of each one of those, a, take the cube root of a, and it becomes a plus b. Times, now we have to multiply something here that equals a to the third plus b to the third. That is a squared minus ab plus b squared. The difference of perfect cubes factors to a minus b times a squared plus ab plus b squared. Excuse me, b squared there. So just to review, to factor, and I'm going to do a couple of problems here. It's going to be very helpful for you for not only this class but SATs, to recognize three things here. One of them is a plus b squared. Another one is a minus b squared. Then this one is a difference of a perfect square. That's 1, 2, and 3. And then the next two that you want to look for by inspection are perfect cubes. The perfect cubes look like a to the third plus b to the third, a to the third minus b to the third, and these are how they factor out. So that said, I'm going to turn the page here and do a couple of example problems for you to be able to see. Hang on. So let's take number 1. Take a good easy one, but it's a good example. Number 1 on page 185. So it says factor 16x to the third minus 64x to the second. So factoring means to go the other way. We are not expanding this or multiplying. Factoring is to go the other way, so to speak. So I want to know the factors here. In other words, a factor is what times what equals 16x to the third minus 64x squared. Now, if you look backwards or look in the book, you'll see that we're dealing with some special polynomials here, and we're trying to get you to recognize those three perfect squares and the two perfect cubes. Now, even though this has a perfect cube here, one of the first things that you want to do is take out a common factor, or factor out a common factor here. And I'm going to spend a little more time on this one. And if you look, does 16 have a common factor with 64? Yes, it does. Does x to the third have a common factor with x to the second? Yes, it does. So we want to factor that out and make our life easier. In fact, 16 goes into 64 4 times. So I can factor out a 16 here. It's a common factor to both. And I can factor out an x squared. If I do that, I am left with x here minus 4. And that is number 1 factored. Now, let's go to one that requires one of those special ones like number 4. And again, the recommendation here, actually it's not a recommendation. The way to do this is, look, inspect it, look at it, and see what form it seems to come in. So let's look at this. This has a z squared term. By the way, these are always written in terms of descending exponents. So you write the highest exponent to the left and then the next one. And you notice that this is a squared term. This is z to the 1, and this has no z term, which means this is going to be one of these up here. This is either going to be a minus b squared, a plus b squared, or a minus b times a plus b. So how do you know which one? Well, this is always ends up with a difference of 2 squares. And these two, this is not. This is not a difference of 2 squares. So this does not work here on this one. So this has a negative term in it. The only way we can get a negative term is we have a hybrid of these two. Okay? So this is a minus something and a minus something, because in this last term, if we multiply these two, a negative times a negative always equals a positive, and then this sum we have to figure out to be a negative here. So this first term here, let me grab a different color so that this is a little more clear here. This becomes, let's get a different, excuse me, let me get a brighter color here. This becomes, I don't know why this won't do it, hang on a minute. This becomes z here. And of course, we have z over here. And these both need to be negative, because if we had, again, over here, if this question mark here is negative and this one is negative, when we multiply them, they get a positive, and we have a positive here. So look, we have negative 6 times negative 6. So FOIL this. Z times z is z squared. Z times minus 6 is minus 6z. Minus 6 times z is minus 6z. Negative times negative is positive. So that's our answer. Our answer here is z minus, 6 squared, and that's factored. So let me turn the page here and go to another example. Let's look at number 11 on page 186, which is 121 s squared minus 66 st plus 9t squared. Looks complicated, right? First thing, is this squares or perfect cubes? It is squares. So that means that we know this is going to be a combination of either a plus b times a minus b. We know that's not going to work because that always results in a difference of 2 squares. So that is not this. So this has got to be a combination. And we see again that we have the last term is positive, the middle term is negative. So that means this has to be s minus something and s plus something. And these are both going to be negative. And as it turns out, of course, 121 is a perfect square of 11. And this is 11. And the perfect square of positive 39 squared is negative 3t. So this actually looked complicated, but it's not. So this actually factors to 11s minus 3t all squared. Let's look at another variation. Here is number 15. 15 is st squared minus s. Again, this is a squared term, but you'll see that this last term isn't a perfect square. It doesn't seem it. But again, on the first problem I said always look for a common factor, and there is one. There is s and s. So if I take and factor out an s, I'm left with s times t squared minus 1. This is a light bulb moment, because That is a difference of two squares. So we can now factor that. The difference of two squares is, remember, a plus b times a minus b is a difference of two squares. In this case, that is t minus 1 times t plus 1. And that is the factor of number 15. Okay, let's look at number 17, and then I will have given you just about every variation here. Number 17 is t to the third minus 27. Okay. Immediately recognize that we cannot factor out a common factor between t to the third and 27. Can't do that. And then hopefully you recognize that's a perfect square, and that's a perfect square. 27 is a perfect square because it's 3 times 3, which is 9 times 3, which is 27. So that makes this the difference of two perfect cubes. Now, go back to page 184, and as you get started here, a difference of perfect cubes factors out to a minus b times a squared here, and the b squared term over here, and its opposite. When we factor the negative here, the middle term is plus ab. So, whoops, I don't need that parentheses there, sorry. The parentheses is over here. So how does this compare here? And to make it easiest as possible for you, make this the same thing as here. So we have t and we have 3. So take this over here and say t minus 3. Then take the squared term, t squared. Take the last term here, which is 3 squared, which is 9, and take the positive product of these two terms. The positive product would be plus 3 times t. And that is how that is done. And again, that's number 17, page 186. So I've given you some examples, and hopefully this will be some help.